So we have started to look into the turboprop engine. We start with the overview of a turboprop engine and then going through the historical background and the milestone of a turboprop engine, how it's all started until the current or the recent usage of turboprop engine in modern transport, especially the military type of aircraft. And before the break, we look into the thermodynamic analysis of a turboprop engine. Okay, and now we shall continue the remaining subtopic. We will first look at the equivalent engine power. With regards to the equivalent engine power, there are two conditions. One is at the static condition and the other one during flight operation. So we will look into what are the corresponding equations involved to find the equivalent engine power. The two flight phases will be discussed, static run and the cruise conditions. The first one is static condition. During testing on the test bench, okay, normally the type of engine or turboprop engine will be tested in the laboratory or at the test facilities to ensure that what are the whether the engine can operate by design or it is need to be further modified. So during the testing or takeoff condition, the total equivalent horsepower, we call it as the TEHP, total equivalent horsepower, and is equal to the SHP, the propeller plus the SHP equivalent to the net thrust. For estimation purposes, it is taken that under sea level static conditions, one shaft horsepower, okay, is equivalent to approximately 2.6 pound of the jet thrust. So you have expression 713A here. The total equivalent horsepower during takeoff is equal to the shaft horsepower plus the jet thrust. That's 2 points jet thrust over 2.6. One SHP is equivalent to approximately 2.6 pound of the jet thrust. If you would like to go into the SI unit, experiments have shown also that the total equivalent power, TEP in kilowatt, is related to the shaft power, SP. Just now we look at the shaft horsepower, SHP, which is also being given in kilowatt by this relation, where we have expression 713B, the total equivalent power TEP in kilowatt at the takeoff condition is equal to the shaft power in kilowatt plus jet thrust in Newton over 8.5. Okay, because 8.5 is equivalent to 2.6 pound, which is equivalent to 1 shaft horsepower. The thrust on the test bench or the ground testing or in the during takeoff is given by this expression, right? So you have the thrust produced equal to the mass flow rate of air coming into the engine times 1 plus the fuel to air ratio F minus B times the UE, the speed of the exhaust velocity. Now let us move into the another condition, and the flight operation. For a turboprop, during flight, the equivalent shaft horsepower ESHP is equal to the shaft horsepower plus the jet thrust power as the following relation. So ESHP, equivalent shaft horsepower, equal to the SHP, shaft horsepower, plus the thrust times the velocity of the aircraft speed, divided by a constant time the efficiency of the propeller, right? We know that the thrust itself equal to the mass flow rate times this expression, which we have already seen in our previous slide. Okay, so you can then get the equivalent shaft horsepower using expression 714A, right? The constant for in equation 619A, okay, depends on the employed units. Thus, the depending on the unit that you are using, whether it is velocity in feet per second, thrust in pound, or you are using miles per hour, all right, or you are using knots and inches a feet per second, so you can using different constant, right? So depending on the type of units, okay, 714B, right? So this constant equation is actually not equation 619A, is actually equation 714A, right? There's a mistake over here. Normally, a value of the propeller efficiency, zeta PR, is roughly around 80%. We can, which is employed as the industrial standard. So very rare we have a very high propeller efficiencies, 99% or 95%. So normally they will take it as 80% propeller efficiency. Right. Let us move into 7.2.5, how we are going to look calculate the fuel consumption for a turboprop engine. As previously explained, during the past 3 weeks, we look already for turbojet and turbofan engine. The fuel consumption is defined as the thrust specific fuel consumption, TSFC, which is defined as TSFC equal to the m.f, mass flow rate of the fuel, over the thrust. Okay, the thrust specific fuel consumption equal to the mass flow rate of the fuel over the thrust itself, and expressed in terms of kilogram fuel per Newton hour. All right, that is what we have already seen in our previous chapter number 6. For a turboprop engine, the fuel consumption can be identified by what we say as equivalent specific fuel consumption, right? ESFC, right? Okay, and then it is actually being defined as equal to the mass flow rate of the fuel over the equivalent shaft horsepower, ESHP, and being expressed in the following unit. You can have it in kilogram fuel per kilowatt hour. Typical values for equivalent specific fuel consumption are around 0.26 to 0.36 kilogram fuel per kilowatt hour, depending on the type of the turboprop engine. Let us go through one example. Okay, since we have time today, we can go into example 7.1. A two-spool turboprop engine. Okay, once we put a two-spool, you can have you have to put in your mind that there are either two set of compressor or two set of turbine, and the low pressure turbine is connected to either the low pressure compressor and the propeller, or the other type of the other high pressure turbine is connected to the high pressure compressor. And this is just one of the possibility. All right. See, so the two-spool turboprop engine with the propeller driven by a free power turbine is considered. In this particular case, it is required to calculate the equivalent shaft horsepower, ESHP, and the equivalent specific fuel consumption, ESFC, in the following cases. One is the static condition, given that the mass flow rate for the fuel is 1,500 pound per hour. The thrust is 600 pound fuel, and the shaft horsepower is given by 2,800 value. And the second condition is the flight condition, where we have the velocity for the aircraft is 330 feet per second. The mass flow rate for the fuel is 1,000 pound per hour, and the thrust produced is 300 pound fuel, and the the shaft horsepower is 2,000. The propeller efficiency is given as 0.8. So this is another condition. So you have the static condition and the flight condition. Don't mix it. You have to solve one by one. For the static or ground run condition, the ESHP, equivalent shaft horsepower, and the equivalent specific fuel consumption can be calculated using the following relations, right? So you have ESHP equal to SHP plus T over 2.5, which is equal to, and you have given SHP 2,800. You are already given the thrust at 600 pound, which is divided by 2.5, and which is equal to 3,040 horsepower. Right? For the equivalent specific fuel consumption, the M.F is 1,500 given already. ESHP, right? You put the value that you already calculated for ESHP into this expression. You can now get the equivalent specific fuel consumption to be 0.4934 pound per ESHP hour. Right? So you already done for the part A for the static condition. For the flight condition, when you want to find ESHP, you have to use the expression, right? Since it is given in the flight speed is given in what is it called? Okay, feet per second. So you have to use 550 as the constant, right? So don't get it wrong or mix. You use a different constant for miles per hour, for knots, and other type of units, right? So this is a common mistake. Okay, you use the wrong equation for different units. Okay, so you can then put in terms of the numbers given. We have already given the shaft horsepower. You already know the thrust. You have the velocity. You have the propeller efficiency. Then you get the equivalent shaft horsepower to become 2,250 horsepower. And then we continue to find the equivalent equivalent specific fuel consumption. I'm very sorry, ESFC. So you have the mass flow rate of the fuel, which is 1,000, and you already got the value of ESHP, which is 2,250 horsepower. You obtain the equivalent specific fuel consumption to be 0.4494 pound fuel per horsepower hour. All right. So this is during the flight. Okay, you can see here, it is not that different. For static condition, it is 0.4934. For during flight, it is 0.449 for equivalent specific fuel consumption. Because you consume more fuel for takeoff or at static condition compared during cruising at flight. Let us go into another example. We have example 7.2. A double spool turboprop engine is installed to an aircraft flying at a speed of 200 meters per second. We have an altitude of 6 kilometers. The condition of the ambient temperature is 249 and the ambient pressure is 0.472 bar. Okay, the maximum temperature, turbine inlet temperature is set 1400 degrees Kelvin, and the fuel heating value Q HV equal to 43,600 kilojoule per kilogram. It has the following particulars. So there are many information given here. Okay, mass flow rate is given 14.6 kilogram per second. The compressor ratio, low pressure compressor 8.5, high pressure compressor pressure ratio 2.35. The pressure for the combustion pressure change in the combustion chamber 2%. Okay, the inlet or diffuser efficiency already given, and the remaining. So you have to take note all of this in order for you to use later on. Even the bleed percentage B is given, alpha also given, specific capacity at constant pressure for the compressor, and then for the turbine and the nozzle also given. Okay, what you need to find, basically it is required to calculate the following. One is that you have to find the equivalent brake horsepower, EBHP. And then you have to find the ratio between the thrust forces generated by the propeller and the nozzle. And finally, finding the optimum alpha. So in terms of the solution, this two-spool turboprop is composed of the following modules. So you have the intake, which is state 1 and 2, low pressure compressor state 2 and 3, coupled from both sides to the low pressure turbine and propeller, high pressure compressor states 3 and 4, combustor state 4 and 5, high pressure turbine state 5, 6, which drive the high pressure compressor, and low pressure turbine state 6, 7, and nozzle is on stage 7, 8. Okay, successive analysis of the elements will be given below. For the intake, if you look at the sonic speed, you want to find what is A, right? So you use the expression to find the speed over there. You get 316.3 meter per second. You can find the Mach number given you already. You have already obtained, already given over A. A is already what you already find here. You can get the Mach number is 0.6323, right? The moment you get Mach number more than 1, meaning that you are putting the wrong values. Okay, so just have a check and common sense saying that turboprop flying less than Mach 1, okay, at the sonic speed. And then you can find the TO2 using the expression for TO2. You get 268.9 Kelvin. You can also find the PO2 for the intake, which is we know that it is equal to 1.0736 PA, right? You already have PA value at 6,000 kilometer. You can now get the PO2. which is equivalent to 0.5067 bar. Moving into the low pressure compressor, state 2 to 3. So you have P03, put the low pressure compressor value, right? And then you get P03 at 4.307 bar, and the temperature at 03 at the compressor state end of this compressor is 542.4 Kelvin, right? The specific enthalpy rise can also be found as 274.87 kilojoule per kilogram. Moving into the high pressure compressor, okay, P04 is 10.12 bar and T04 is 719 Kelvin, right? So this is before it goes to the combustion chamber. In the combustion chamber, right, the pressure, you already been given the pressure drop or PCC value, which is 2%, and you get the pressure at state 4.5 or PO5 9.19 bar, and you can also find the the fuel to air ratio to become 0.0197, considering the air bleed, already given air bleed, which is 0.0821. Okay, you put all the values there, you can get the fuel to air ratio value, F. Going into the state 5.6, high pressure turbine, energy balance between the compressor and the turbine, you put all the expression, putting the numbers, you will get T06 value 1234.7 Kelvin and P06 value 5.726 bar. Okay, combine the low pressure turbine and the nozzle state 6 and 8, right? You will get T8S equal to 661.6 Kelvin and the enthalpy drop equal to 657.938 kilojoule per kilogram. And low pressure turbine specific power, right? So you can put the expression over there. You already given alpha and the remaining of the values that you already obtained, okay? And you can then get T07, which is equal to 718.9 Kelvin, and P pressure at station 7 is 0.68658 bar. The shaft power, which is equivalent to this expression, and the propeller specific power PPR is given by the relation over here, and that leads us to the propeller specific power, which is over the mass flow rate. You get 173.625 kilojoule per kilogram, and that is the answer for the propeller specific power PPR, PPR over M dot A. The propeller thrust is correlated to the propeller power by the relation. So you can get, so you already got the value for the propeller power, specific power. You know the velocity of the aircraft, then you can get the propeller thrust, specific propeller thrust to become 868.12 Newton kilogram. Okay, moving into the nozzle part, the last part, the exhaust gas speed UE can be obtained by the following relation. So you get a UE equal to 353.6 meter per second. The thrust force obtained from the exhaust gas leaving the nozzle is denoted as Tn, given by the relation here. So specific thrust at the nozzle, Tn over m dot, equal to 131.5 Newton per kilogram. Hence, the total thrust, you already got TPR, now you have TN, you can have the total thrust value of 14.585 kilonewton. Total equivalent power, okay, P equal to T thrust times the velocity, you can get 3,911.76 horsepower, and the ratio between the propeller and the nozzle thrust is 6.6 value. Optimum alpha, so you just use the equation to find optimum alpha, and you will eventually get this value of 0.9606. All right, before we end, probably best to go into the last subtopic for turboprop engine, analogy of the turboprop engine with turbofan. Okay, a turboprop engine are analogous to high bypass turbofan engine, and the propeller itself is an unducted fan with a bypass ratio equal to or greater than 25. The airflow through the propeller is slightly accelerated and thus acquire speed slightly higher than the aircraft flight speed, and the momentum difference between the inlet and outlet flow through the propeller produces the propeller thrust. Okay, next, this accelerated air passes through the engine core and accelerated to a higher speed. The momentum difference between the outlet and inlet core flow results in the core of the thrust. The thrust force is given by this relation. You have this expression 716A, okay, where you have the component of the velocity between U1 and U0, okay, and then you have the component of the fuel air ratio and the bleed air, and between the exit velocity and the U1 velocity. Introducing the bypass ratio into equation, okay, again this is a slightly wrong, not 617A, it is 716A, okay, so this is again is wrong, and you get the expression of 716B, putting the bypass ratio value over there, the specific thrust related to the engine core mass flow rate to get to this expression 716C, where for this one is just a thrust, and this is the specific thrust where you divide the thrust with the mass flow rate. Okay, so with that, it leaves us to the remaining subtopic for chapter 7, turboshaft and prop fan, and finally the summary. We shall continue the remaining subtopic next Monday in our lecture number 13. Okay, so my suggestion is that try to go through the two examples, 7.1 and 7.2, so that you can get familiar with the thermodynamic analysis for the turboprop engine.